So looking at single slit diffraction, you'll see it's probably like interesting. You get kind of a pattern that's a little bit like what you see with double slit diffraction or interference, right? So the idea is you get a screen, right? Something like this here, or I guess this here would be your screen, and you get some incoming light sort of represented with these arrows over here, and you have a little slit, right, with a certain width. Now the width needs to be pretty small, right? We're talking like millimeters or whatever. It's not very big at all. And then you have a screen kind of similar, usually about a meter or so away, and you can get a little pattern like this, right, on the screen, which is kind of interesting, particularly when you've only got a single slit, right? So just to look at that, so the requirements for this, right, the number one, right, the width is very small, right, but not so small it acts as a point source. So you've kind of got like a, fine line here, if you will. No pun intended. You've got monochromatic light. That's sort of been the case with all of the stuff we've looked at, right? So you've got a single wavelength, or roughly the same wavelength of all the light. And the screen is relatively far from the slit. And what you see here, what is slightly different, right, is you get sort of that central maxima, which is a little like double the size of the other ones. So let's look at how we might make this happen. So let's look at destructive interference, because that's kind of the interesting thing here, right? That we've got a single slit and we're getting these dark spots, right? We can understand why we would have light spots because we've got light going through this slit. So just, the dark spots are kind of the interesting part here. So what we do is for a situation like this, we say, okay, let's take a top view, right? So that's really what we're looking at in part B here. Right, so just to be absolutely clear here, right, this is a top view of this situation over here, right? And so what we're looking at here is we're looking at the opening, right, the width of that slit, right? So we're looking down on it. And what we do here is we say, okay, let's just separate this into two parts. We'll just call them A and B, right? And so the length of this first part that we're calling A is W over 2, right? It's half the width. And then the second half that we're calling B will also have the same width or whatever, right? W over 2. And we can look at how light from the first half that we're calling A interferes with light from the second half we're calling B. And note that for any point, so like we're starting this right, so point A is actually in the opening, right? It's not on the line. So it's like if the very first point of space as soon as the opening goes. And we can divide this into as many as we want. This might go to like, A billions of billions of billions, right? And so the point B is exactly half the width away from that. And you would go all the way until you get to the very last A right in front of B, and then the very last B would be right here, right at the very end. So if there was one little infinitesimal spot after that, you would be, right, no light would get through there. So that means we can look at however A1 interferes with B1, which should be the same way that A2 interferes with B2, right? Because they're the same width apart. So that means we can look at something over here where we're just looking at A1 and B1. And just like when we looked at double slit interference, we can say, well, they're kind of separated by this length that we're calling W over 2. The screen is far enough away that we can regard this path here, and this here, right, which is technically drawn that way, but when it's far enough away, they're basically parallel, right? They're so far away that when you actually looked at this, right, the screen is all the way over here, and you know the width of your opening is really, really small, right, comparatively. So if you've got some point here, essentially, right, they're two parallel lines, right? So if we look at that way, then that means we can look at this and say, okay, well that's a right triangle here, and we can say the sine of theta is this extra bit here that the one that light from B has to travel, so that's that extra bit that we'll call delta L, and the sine of theta then is delta L over the hypotenuse of that triangle, W over 2. Multiply both sides by W over 2, and you get that. Very similar to what we had before, only we're writing this as W over 2, not the distance between the two slits. And from that, we can actually figure out what the interference needs to be, right? Because we're just saying that all the light that's coming from the B's have gone that extra bit, right? W over 2 sine theta. So if we're going to have destructive interference, then delta L needs to be equal to whatever the wavelength is divided by 2, right? So that the waves coming from B have gone an extra half wavelength. Right now they're going to interfere destructively. And then we can replace delta L with that equation we just had up above, W over 2 sine theta. And then we can rearrange this so that we get sine theta is lambda over W, right? Whatever the width of this opening is. Then, so that's that, right? We have our equation. We know how to find the angle that will give us this destructive interference. Then we can continue this, right? That was fun. So let's do it again. Only now, instead of breaking the width of the slit, so this is once again a top view, instead of breaking it into 2, let's break it up into 4, right? And we can have the same thing where we can have this first part we're calling A and the second part we're calling B. We can just look at them the exact same way we looked at them before, right? And then we'll have the same thing also happening with C and D. So if we want to look for destructive interference, we'll just look for destructive interference between all the waves coming from A and B, and then that should also be the case for all the waves coming from C and D. So if we just look at A and B, again, it'd be the same thing, right? We can look at A1 and B1, and the ones from B1 will go this extra little bit delta L. But now, doing the exact same trig we did before, right? Just looking at this triangle here. Let me get a different color so it actually shows up. Right, looking at this right triangle here, we get sine of theta is delta L over W over 4. So when we rearrange that, we end up with W over 4. And we need this to get destructive interference, the waves coming from B need to go an extra half wavelength. That's the lambda over 2. And we can actually rearrange this, in this case, do it right here. And we end up with W sine theta equals lambda over 2. Or I did it here on the bottom, right? You do the same thing. And you end up with a very similar equation to what we had before, only now you'll notice it's 2 lambda over W, right? And you can see on the last one we looked at, it was just lambda over W. And if we compare these here then, right, we can say, well, if we continued this pattern then, right, we could divide this thing up into, here we divided it into 4, right, twice as many. So if we divided this thing up into, 8 or whatever, right, we could continue this pattern and we should get this equation right here. We can just generalize this. Right. And this is again saying we have any number of pairs that we can put these in. Now this seems great. But you'll notice I kind of skipped something, didn't I? We had 2, then we had 4. What about 3? Right? What if we break this thing up into 3 parts? We didn't consider that. So let's look at what if we do this with 3 parts? Right? Well, we'd have to break this thing up into A1, A2, A3. So there could be A1, that's roughly a third here. That would be B1 and dot dot dot. And this here would be C1. Right? Dot, dot, dot. And so what we're looking at here is the light from A and the light from B. Yeah, I'll leave it like that, right? We want to look at destructive interference here. So we've got the light from A and the light from B. We can make this into our right triangle just like we did before. And we can say this side right here, this is W over 3. And so this part right here, this little bit, this delta L, we can say sine, and that'll be our angle here, theta. Sine of theta equals delta L over W over 3. All right. Which of course we can multiply both the top and bottom by 3 if we want, and we can say, or I'll just move it over there because I think that's generally what we want. And if we want destructive interference here, right, we've got delta L has to be some multiple of, or lambda over 2. Here's what I just did up above, and then we get this equation here at the bottom. Right? But if you look at this, there's something interesting that happened here, right? I just looked at all the waves from A canceling with all the waves from B, but what about C? Right? There's nothing to cancel the waves from C, right? All the waves from A and B cancel with each other. They interfere destructively. Okay, fine. But now we get all these extra waves from C. So this actually corresponds to a bright spot on the screen. And I think I wrote that in there. And since this can be any multiple of this, right? If we break this up into any odd number of segments, right? So there we broke it into 3. We could equally break it into 5 or 7 or 9, etc. That's sort of what I've indicated here. Then we should get that same phenomenon, and then we can express this more generally with this equation here. So again, like earlier today when we're looking at interference in thin films, right? You get very similar but different equations, and you really have to look at the situation and think, okay, what do I want? Do I want a bright spot or do I want a dark spot? And then that sort of determines what equation you use, right? So you have to look at the situation. You can't just plug it in. And then here, if you get, this is just a general what this sort of thing looks like, right? We get that central bright spot in the middle, and then as it peters out, you can see these here, right, which correspond to the equation we just had, where you get these dark spots here. So why not try and use this? Let's look at an example, or you try the example, and then we can take it up. So yeah, here it is, like just drawing it for you. With light from a laser pointer with a wavelength of 670 nanometers. Remember, nano's 10 to the negative 9. passes through a slit with a width of 12 micrometers. So whenever you see that symbol there, remember that's micro, 10 to the negative 6. And the screen is 30 centimeters away. So we've got a lot of different units here. So we want to know how wide the central maximum is in degrees and in centimeters. And so here's you can see the light or whatever. I've indicated the width of the slit and the length here from the slit to the screen. One thing to note here, though, and this is actually kind of important with this phenomenon and how it's a little bit different, is these points or these angles, right, are all relative to this central maxima, right? So we've got this brightest spot here right in the middle, and then we've actually got this distance here, which I guess I could indicate this is like, right, this distance here we'll call x1, and we've got that on both sides. So really the central one is twice as wide, right? So what I was going to do here then is just figure out this angle theta, right, which is just from the center line to the first minima, and then I'll just double it because I know it's going to open on in both directions, right? So I said, well, the first minima, we can use that equation we developed where it's just sine theta equals lambda over w, or it was like, there might have been an n here, right? But it's the first one we want, so n is just 1. I can rearrange that, right? We need to take the inverse sine of both sides to get the angle, and I put in the numbers there for lambda and for w. Note that, yeah, like I put both of them into meters so that it was consistent, and then that gives me an angle of 3.2 degrees. So if I want to tell you the central maximum in terms of degrees, well, it's really going to be double that, right? Because it's going to be that same angle here as well. So I could say, therefore, theta 1 is just 2 times that, which would be 6.4 degrees. And then it also asks for this in terms of centimeters, which is what I was just working on there. So basically, I want this distance x1, and I'll do the same thing. I'll just double it. So if I'm looking at this triangle, right, it's the tangent of theta that is x1 over L. So that's what the equation I wrote down here, tan theta equals x1 over L. Multiply both sides by L, and then I just substituted in the numbers, and I got 0.01677 meters. So I guess where I left off here, therefore, x total here would just be double that, right? 2 times 0. Whoops, there's another 0. Which you could write as 335, I guess, if we're just sort of rounding, or 3.35 centimeters, right? Because this one here is in centimeters. So just to make it a number. There's a part B here. What is the separation of adjacent minima, right? So excluding the pair on either side, right? So we've calculated this central maxima, and we've said, okay, that's 3.35 centimeters, right, along the screen. So what's the distance from, let's say, here to there, and then from there to there, right? And as we keep going, or if we were on the bottom, right, from the first one to the second one, or the second one to the third one, what is that distance? And if you look at the equation, right, we would start with the same equation. The only difference is we would just keep putting in, for the n here, we'd put in 2, and then 3, and then 4. So they're all should be the same distance as the first one from the center, right? So for part B, we can say all other minima are this here, right, which is just 1.677 centimeters. let's say, apart. As I tried to draw it up there.